So welcome to this second session to the electronic configuration. But before we continue on, I would like to just go over a quick revision on what we did last time. So last time, basically, we were looking at the construction of the atom, and the atom basically we said it's made of the nucleus. The nucleus, we have the protons and neutrons in it, and then you have the electrons around it. So the electrons, they'll be concentrated or they'll be located in the space around the nucleus, and in specific in subshells, and these are called S, P, D, and F. And you remember last time we spoke about these energy levels, and we said here 1, 2, 3, 4, 5, 6, 7. These are representing the energy levels, or in other words, we call them shells. And these shells or energy levels, main energy levels, they contain subshells. So the energy level number 1 contains the subshell S, and it takes number 1 because it's located in the energy level number 1. And then energy level 2, it basically has the it has S and P, and this S we call it 2S, and this P we call it 2P because they are both located in this energy level number 2. And if we take number 5 here has the subshells of S, P, D, and F. And the S here is different to the S here, that it has this number, which is the number of the main energy level or the shell. So this is number 5, this is number 5, this is number 5, and this is number 5. So basically this S has the lowest energy, and this S has the highest energy. So if we want to distribute the electrons around the nucleus, we have to follow 3 rules. And these are the Aufbau principle, Hund's rule, and Pauli exclusion principle. So last time we explained that, and briefly I will recap on this. So the Aufbau principle says that if you want to distribute the electrons around the nucleus using these energy levels, then you have to start with the lowest energy level before it's filled in, and then you go to the second energy level, and then you go to the third, etc., etc. So you put your electrons in the lowest energy level, then you go further, energy level that has more energy than the first one, and then you go here, and then here, and then here, and then here, and then according to the order that we have created last time. In case of Hund's rule, Hund's basically says that when you want to distribute the electrons, you should distribute them as single electrons first. So when we go to P here, P, as you know, it can take maximum of 6 electrons. So S can take maximum of 2, P can take maximum of 6, D can take maximum of 10, and F can take maximum of 14. So basically, if we want to distribute the electrons in P, so all we need to do is as follows. So for the P electrons, we go, imagine we have 5 electrons, we want to distribute them. So you may think that you can do this. And this is the wrong way. The right way of doing it is as follows. 1, you distribute them singly, and then you pair up the remaining. 1, 2, 3, 4, 5. Okay, so you may say, okay, so it's the same result. Yes, same result, but imagine that you have 3 electrons instead. So here we have 3, electrons. I will do it in both ways. So the first way, that you will pair up from the beginning. So 1, 2, 3. This is wrong. Second way, that you will do it as 1, 2, 3, and that's correct. So always do it this way. Now, just a quick reminder also, we said that these subshells, S, P, D, and F, they can be represented using so-called electron in boxes. So the S is always represented as one box and can take maximum of 2. And then the P is represented by 3 boxes, and each box can take maximum of 2. And the D is represented by a box with 5 boxes inside. 1, 2, 3, 4, 5. And each box can take 2 maximum. And then the F can be divided into 7. 1, 2, 3, 4, 5, 6, and 7. And each of these can take maximum of 2. Okay, so as we said, this is the energy level, the N number 1, 2, 3, 4, 5, 6. So we call this energy level. The energy level has another name, which is shell. And then the S, P, D, and F, we call them subshells. So this is S, this is P, this is D, and this F, and we call them subshells. And these individual boxes, this one, this one, this one, this one, we call them orbitals. Okay? So this is basically the classification of the subshell, the main shells or energy levels, subshells, and orbitals. Okay, so that was the second rule that we have to follow. So the first one was that if we want to distribute the electrons, we have to basically fill the electrons in the lowest energy level in the subshells, and then we'll go beyond that. The second rule, which is Hundred's rule, says that you have to distribute the electrons as single electrons before they pair them up. And finally, Pauli exclusion principle says that there are no 2 electrons with the same spin can be available in the same orbit. So basically, as we said, the electrons, just to clarify this point, the electrons, just I'm trying to get the pen here. Yeah. So the electrons, as you know, they are basically a charged particle, and charged particle basically it can behave as a magnet, as creates a magnetic field, and the magnetic field basically it has a direction. So this direction can be upward or downward. Fine. So the Pauli exclusion principle says that there are no 2 electrons. There are no electrons can have the same direction, same spin, and these that are available in the same orbit. So if you have an orbit, which is one of these boxes, it must have, if there are 2 electrons in it, these 2 electrons must have 2 different spins. One of them upward and the other one downward. Okay, you can't put 2 electrons in the same orbit, in the same box here, and they should look like this. Okay, or like this. So this is wrong, and this is wrong. They should be upward, and one of them downward. Okay, so this is the correct way of doing it. Fine. So these basically, in brief, the main things that we discussed last time. Here we looked at some examples last time. Some examples on how to distribute the electrons in the electron shells. and subshells. Now, the main thing here is that you need to be capable of writing down the energy ladder. So the energy ladder is this one. So if you follow this diagram here, the energy ladder basically it goes from 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4s, 5s, etc. So again, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6d, etc., etc. Okay, so you must basically follow this order in order to fill in your electrons. Okay, just try to get rid of this. Fine. Okay, so trying to get rid of this. It is not. It is. Okay, so the next thing we need to learn today is just a completion of last time's lesson, which is learning a few exceptions of what we learned now, of how to distribute the electrons, and also giving you guidance on how to study it. Okay, so here is chlorine, for instance. So chlorine has 17 electrons. If you want to distribute them based on the order that we have created earlier, so it will be 1s2, 2s2, 2p6, 3s2, and 3p5. The total must be 17. As you can see, p here, it took the maximum number that it can take, which is 6. 2 has taken the maximum number that it can take, which is 2. So the total here, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and the remaining 5 went to 3p. These are examples. Also, you should have completed them. I hope that you have completed them and you have got them correct, have got the correct answers. And also this physical classroom test. Basically take this test, and then you need to post the scores on the WhatsApp. Fine. The next thing here, again, we have posted some more examples, because in the exam you can be asked to do the electron configuration of the electron in boxes. So this is this sort of way of doing it. This way of doing it, you will be asked to do the electron configuration using the notation of S, P, D, and F. So you do it this way. If you were asked to do the electron configuration in electron N boxes, so as you can see, electron N boxes, that's why it's called electron boxes. Fine. So the next thing here is exception to the rule. Now, there are a few exceptions here, and what we will be concerned about in according to specification and according to this level are mainly two elements, the chromium and the copper. So the copper here is 29, and if you see, if you want to do the electronic configuration of the copper, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. This is basically how you will do it if you followed the same rule that we have explained earlier. But instead, for the copper, we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then 3d10. Okay, so it's not 4s2 and 3d9. And the reason here that this orbital is half filled and this orbital is full, because this basically gives this element further stability or higher stability than as compared to we put 2 electrons in the s orbital here and 9 electrons in the d orbital. Okay, so energetically, this configuration is more favorable by this element. The other element that is doesn't follow the rule as well is chromium. And for the chromium, I would like you to search it and to write it down. And during the next class, the Q&A class, I will basically look at your answers to check it. Okay, so this is, again, sort of a homework for yourself to look it up. These elements, I just put them here for your knowledge. You're only responsible for the first 36 elements in the periodic table. So you're not responsible for these elements, but just I put them here for your knowledge. Okay, so here just a recap of what we did about the F-Bell principle. That means we need to start from the subshells or shells with the lowest energy level, and then we go further. The electronic configuration of chlorine that we have already completed, the electron spin, that one of them has to be pointing up and one of them has to be pointing down. We cannot put 2 electrons of the same spin in the same box. This will be not allowed. So what you need to do is basically when you draw the electrons in boxes, you need to draw an electron pointing up, another electron pointing down. Just like that. And this is called the Pauli exclusion principle. And finally, the Hund's rule says that there are no 2 electrons. If you want to distribute the electrons has to be distributed as single electrons, and then they will be paired up. And as you can see in each of these rules, we have also included the definition that you should learn. Okay, now before we end, just let's take this example. Now, in case of chlorine, here we have chlorine or Cl atom, and here we have Cl minus. So this is the chlorine atom, and here chloride because it has a negatively charged ion. Okay, so what's the difference between the two? I'm sure that at this grade you are aware that if the atom loses electrons, it becomes positively charged. And if the atom gains electron, it becomes negatively charged. So why is that? So let's just explain this point, just in case if it is not clear to everyone. Okay, so imagine that you have a neutral atom. A neutral atom, it means that the number of protons are equal to the number of electrons. So here you have protons, neutrons, and electrons. So this atom basically has 5 protons and 5 electrons. So the overall charge is 0. That means this atom is a neutral. Fine. Now, if I can't basically play with the number of protons. Number of protons is fixed. Now I can change the number of electrons. The number of electrons can increase and can decrease. So let's check two scenarios. First scenario, that we will increase the number of electrons here. So we'll have the same atom with number of protons 5. That means 5 positive charges. And whatever number of n, we're not really concerned about it, because when it comes to the total number of charges in the atom, we don't look at the number of neutrons. And here we have, as I said, we want to add an electron. So here, instead of 5, we'll have 6 electrons. The atom has gained an electron. So what will be the total charge of this atom? Here we have plus 5, plus 5 protons, and here we have minus 6. So the total charge here is minus 1. Okay? And this is a negative ion, or we call it anion. Now, on the other hand, the atom can lose electron as well. So if we have here 5 proton, and here we have number of neutrons, and then here we have, instead of according as compared to the original neutral atom, here we had 5, so here we'll have 4. That means 1 electron has been lost. So the overall charge on this atom is, here you have minus 4, because you have 4 electrons, plus 5, because you have 5 neutrons. They are positively charged. So the overall charge is plus 1. So as you can see, we have 0, minus 1, and plus 1. So always remember, whenever the atom gains electrons, it becomes negatively charged. Whenever the atom loses electrons, it becomes positively charged. Okay? It's just if you want to remember, it's just the opposite of what you think about gain and loss. Always we think that gain is positive and loss is negative. But in case of atoms and the case of their charge, it's the opposite. When the atom gains electron, it becomes negatively charged. When the atom loses electrons, it becomes positively charged. Okay, good. So let's say here this example about the chlorine atom and the anion. Okay, so in this case, here we have 17 electrons. So 1, 2, 3, 4, 10, 12, 17. Now, when it says Cl minus, that means 1 electron has been gained. Yeah, that's correct. Has been gained. So 1 electron has been gained. So where this electron will go, basically you have to add it on the empty shell here. So the electronic configuration of Cl minus will be 1s2, 2s2, 2p6, 3s2, 3p6, not 5. Fine. Here we have left for you a few elements, and you should do them. Pause the video, do the elements, do the electronic configuration of the elements, and then on the next slide, you can compare your answers to the answers on the slide. Okay, so this video will be followed by the ionization energy, and also we will make another video to solve problems about the electron configurations and ionization energy. So there'll be 2 videos after this, one about ionization energy and one about problems in relation to the electron configuration as well as ionization energy. I hope that was beneficial to you, and I will see you soon.